Pulsar Bay Area Meetup. My name is Carolyn King. I'm the head of growth here at StreamNative, and I'll be our MC for today. I want to start by saying we're really excited to be co-hosting this event with Uber and Ververica, and we'd like to thank our MC, Girish, and our speakers from yesterday. So Peter, Kurt, and Nang, thank you for your amazing presentations. I know there was a lot of engagement and a lot of Q&A at the end, so really excited to see that. With that, we'll take a look at the agenda for today. I'll kick us off today, followed by Shuyi Chen from Facebook, speaking on streaming SQL at Facebook. And then Marta Paes from Ververica will be presenting SQL for Pulsar folks. So we'll have a couple of minutes at the end of Shuyi's talk for questions. I encourage you to put your questions in the Q&A box so we can track those. And then we'll have a longer Q&A after Marta's talk. So I know we have a lot of, I know we have a lot of the Flink community here. So I wanted to just give a brief intro to StreamNative and to Pulsar. We'll start with a brief overview of Pulsar. So what is Apache Pulsar? Apache Pulsar is a cloud-native messaging and event streaming platform. And today we're seeing a lot of companies are adopting Apache Pulsar for a number of reasons, but two driving factors are the fact that it is cloud-native and that it's built for containers. So it works really well on Kubernetes. Now, when people think about Pulsar, they often think of it as a Kafka replacement. And in many cases, that's true. But it's important to note that Apache Pulsar serves both data streaming as well as message queuing use cases. So we're actually seeing a lot of adoption coming not just from data streaming use cases, but also from message streaming as well. And we've seen a lot of really exciting adoption stories over the past couple of years. Here we have a quote. This is actually from Splunk's conference in September of 2020. And we have Sundar Sulakumar, who's the CPO of Splunk, saying, "We've shifted to Apache Pulsar as our underlying streaming. It's our bet on the long-term architecture for enterprise-grade multi-tenant streaming." So really exciting to see top companies such as Splunk moving to Apache Pulsar. And here we can see Splunk is not alone. We've seen a massive growth in the adoption of the adoption of Pulsar globally over the last couple of years. So with that, I want to take just a couple of minutes and introduce StreamNative. So we are powered by Apache Pulsar and soon Flink, which we'll talk about in a couple of minutes. We offer a cloud-native real-time messaging and streaming platform. StreamNative is built for Kubernetes to support both multi-cloud and hybrid cloud strategies, and we're founded by the original developers of Apache Pulsar. And now an overview of the StreamNative offering. So we do have both cloud-hosted and cloud-managed solutions, and we also offer StreamNative professional services. Again, just a brief overview here. If you want to find out more, you can visit our website. And here's an overview of the StreamNative offering. As you can see, a lot of people are adopting StreamNative for application messaging, data pipelines, and real-time contextual analytics. It's also important to note that we're available on all of the major cloud providers from AWS, GCP, Azure, and Alibaba Cloud. One of the things you've probably noticed, there's a lot of synergies between Pulsar and Flink. And so at StreamNative, we've started to work much more closely with a team over at Ververica, and we are now cloud partners working very closely together. One of the things that's really exciting with Pulsar and Flink is that it enables us to offer both stream storage and stream compute for a complete streaming solution. And with that, I'll wrap it up. But definitely as the head of growth, I'd be remiss not to mention a number of the really exciting events that we have coming up in the Apache Pulsar community. So we have 3 global summits this year. The first one is happening, it's virtual, but targeting North America, and that's on June 16th and 17th. The CFP for that is now open. So if you'd like to give a Pulsar talk, we encourage you to apply. Registration is also open. So definitely join us and sign up on the Pulsar Summit website. This year, we're also doing the first ever Pulsar Hackathon. We just announced this a couple of weeks ago. This will be taking place on May 6th and 7th. It's a global virtual event, so everyone is welcome to sign up for that. And then I want to take a minute to mention some monthly virtual events that we launched in 2021. So now monthly, we have an Intro to Pulsar 101. This is a really great free 1-hour webinar that enables you to really learn kind of some of the basics and the foundations of Pulsar. And that's actually happening next week, March 24th at 12 p.m. PT. We also do monthly project updates with CJ Gua. The next one will be April 14th at 12 p.m. PT. And then we have monthly office hours with Addison Hyam, and that will be April 21st at 12 p.m. PT. In addition to that, we would love to connect. You can join us in the Pulsar Slack channel, subscribe to the Pulsar newsletter by StreamNative, and also check out, we have quarterly instructor-led trainings for Pulsar fundamentals, developer, and operations. You can find out more on our website. So hopefully that was a brief but interesting intro into both StreamNative and Apache Pulsar. And with that, I would like to introduce Shuyi. If you want to join us, I will go ahead and hand it over to you.
Thanks a lot, Kevin. So let me project my screen.
Okay, great. And I'll give you just a brief intro. So Shuyi Chen is a software engineer working on streaming infrastructure at Facebook. Before Facebook, he was the tech lead of the streaming processing team in Uber data infrastructure, where he built Uber's real-time complex event processing platform for the marketplace. She has years of experience in storage infrastructure, data infrastructure, and Android and iOS development at both Google and Uber. So with that, you can go ahead and take it from here.
Can you stop sharing? It says I cannot share screen while
Oh, of course. Here you go.
Thank you. Just to double check, can you see my screen?
Yes, looks good.
Okay, great. Yeah, thanks for the introduction. Today I'm going to talk about the topic streaming SQL at Facebook. So my name is Shuyi Chen, and I'm a software engineer in Facebook. And also, before I was working Uber, as Karen suggested, and I'm also a Flink and Pulsar committer. So for this talk, I'm going to cover the following topics. First, I'm going to talk about the stream processing in Facebook. And then I'm going to talk about a new stream processing platform that we are building in Facebook called Xstream. So also we are going to introduce some of the key effort in Facebook that Xstream is built on top of. In the end, I'm going to briefly summarize the future work. So first, let's talk a little bit about the background of stream processing in Facebook. So Facebook started the stream processing development actually since very early, back 2014. Puma is Facebook's first SQL-based stream processing platform that is developed in 2014 start. And so it's a JVM-based platform, and also it offered a very SQL-like language to actually allow user to compose their stream processing logic using this Puma query language we call. And also it's a fully managed service. Basically it's similar to AthenaX that is talked about yesterday by the Uber engineers, and it's also fully managed and offered a nice UI for people to compose their job. And currently it supports a few thousand jobs running in Facebook. And another platform that we built in Facebook is called Stylus. So Stylus is a low-level stream processing framework that is written natively in C++. So as compared to open source, it's actually quite similar to Apache SAMSA's low-level API. Basically, it provides the basic building block and the for you to write stream processing processors. So the basic component of Stylus is basically a stream processor. And so you can compose multiple stream processors in C++ and then collecting them using a message queue to build actually a stream processing DAG. So while Puma offer a nice user experience, I mean, like through the web UI and all the fully managed experience for developing PQL based stream processing job in Facebook, we also see many limitations as the the time evolves and the use case evolves. So for example, like Java support is very limited in Facebook. So most of the high performance backend storage service are all written in C++. So that makes integration for Puma with other like storage and service backend difficult and also inefficient. Just to give an example, so the state storage backend that Puma uses actually does not have a native Java client. So in order to use that backend efficiently, so we actually have to build another service, native C++ service, and then Puma basically talk to that service through Swift, and then that service talk to the storage backend natively in using the C++ client. So also PQL currently only support a really small subset of SQL features. For example, like only tumbling window is supported. And in the end, like the syntax of PQL is completely different from actually, it's SQL-like, but it's actually completely different from SQL. From the right, you can see a snippet of that. And also at the same time, Stylus, the framework offer all the basic building block actually to build arbitrary high performance native stream processing jobs in C++. It has all the foundational building block like source, sinks, operators, watermark, checkpoint, triggering, timer, and state backend access, all the stuff. However, like many other like low-level stream processing API, it has a very steep learning curve for our user. And once the job is composed, as they get complicated, it's also incur like high maintenance and operational cost. So in the starting, I think like around 2018, so the stream processing team did design to build a new stream processing next generation platform called Xstream. So the focus on Xstream is we want to first achieve the same data velocity that we offer through Puma. And also we want to build the native C++ engine using native C++ to actually for efficiency and for better integration with the FB Facebook ecosystem. And also at the same time, we want to share the same SQL dialect across batch, interactive, and streaming use cases, such that the user can only they can allow them to write the SQL once and then use across different engines. And also writing the SQL dialect, sharing the same SQL dialect is not enough for you to be able to keep consistency across the execution logic, also as well as the UDF logics execution across different engines. So we also want to make sure that we actually have consistency for the actual execution result across batch, interactive, and streaming engine. And in the end, we want this to be a managed platform, so to free user from like all the operational overhead of managing their stream processing job. And we should be able to scale to tens of thousands of jobs on the platform. So to do that on a high level, basically Extreme adopt the following methodology in building the Extreme call engine. And also in this talk, we will be mainly focused on talking about the Extreme call engine. Although there are other aspects of like job management, and then like also the resource scheduler, a cluster resource scheduler that we built in Facebook for managing the stream processing job. So however, this will be out of scope for this talk. So the methodology basically for us to build the Extreme call engine include the following. First, we decide to build Extreme on top of the C++ based stylus stream processing framework that we mentioned before. And also, we will share the same SQL dialect with like a Spark and Presto with the streaming extension added. And also in the also the third one is we're going to adopt interpretation execution for query execution over upfront combination. And I will talk about a little bit more about the journey of that later. And in the end, we will actually build and share the same vectorized SQL evaluation engine with Presto and Spark so that we can have a consistency for execution across different engines inside Facebook. So yeah, and then after that, in the next following talk, I'm going to iterate over all 4 different methodology and how we actually achieve that. So the first one, so basically we decided to build Extreme on top of the C++ based stylus stream processing framework. So the main reason behind that is Stylus has already offered all the foundational building block in stream processing that include checkpoint, source and sink, operators, timer and triggers, all this, and state access. So this is like the reason why we decided to choose that. And also, the second one is we use the same SQL dialect across Presto and Spark with streaming extension. Though the SQL dialect is actually a cross-functional effort in Facebook. We call it the Core SQL. The goal of the Core SQL project is basically to offer a single SQL dialect and framework across different tools in Facebook. Underlying, it basically modernized the Presto SQL language with the SQL 2016 standard. So you can call it like Presto SQL++. So this basically like with one SQL dialect, this basically make moving between different engines easy based off the use cases. And also it bring other extent, with Core SQL, we can bring other extension from streaming and graph SQL into the modernized Presto SQL language. In the end, we also, with Core SQL, we also try to enable UDF portability across engine, which will not be covered right now for this talk. So this talk, we're going to mainly talk about the streaming extension that actually we built on top of Core SQL in order for us to share the same SQL dialect with Presto and Spark. So as we know, in streaming, there are the concept of like window aggregation, like tumbling, hopping, and session windows. Those are actually not available in the SQL standard. So basically, we provide a design here basically to extend the Core SQL with the streaming extension. So here are some of the design consideration. The first, the new syntax extension, we want to make sure that it's first support all the tumble, hopping, and session window in a uniform way. And also, we want to make sure that we use the Presto keywords as much as possible to ensure low syntactic ambiguity with the existing SQL. And then we try to restrict the syntax extension to be only in the table clause, as well as like we provide a way to basically specify the active field instead of implicitly add them, like the window start and window end field for tumbling window, hopping window, and session window. And also we want to make sure that we provide first-class support for the tumble, hopping, and section window semantic. So actually user can easily understand the SQL. And in the end, I mean, we want to make sure that the syntax will be supported by both Presto, Spark, and Extreme for execution. So next, I'm going to quickly go over the syntax that we designed. So first, over the tumbling window. So basically, like just a quick recap. So tumbling window partition event time into equally spaced disjoint and gapless covering intervals as shown in the figure below. So to support tumbling window in SQL, as you can see, we add a tumble on keywords in the in the table clause to explicitly set this the tumble operation, and then you can specify the time where is the how you create a tumble window from the event, and then the duration of the tumble window as well as the offset of the window. Also, you similar to the unless clause, you can explicitly specify what are the added columns after the tumbling window clause. Basically, here you say there's a window star column alias and window end column alias. So basically, after this query, your original table will be generated with two new columns called window star and window end, which is the rows, the window corresponds to the window that the row actually fall in. And then for hopping window, so basically hopping window place intervals possibly overlapping in a fixed size, evenly spaced across event time. So similarly, we design like syntax called like a keyword hop on in the table clause to indicate like a hopping window generation. So one interesting things that we know that is in Facebook, there's a heavy, especially in machine learning, there's heavy use of actually like aggregation of the same event of different like across different window size. For example, like they want to build features across for aggregation for 1 day, 5 day, 7 day as such. So in this SQL clause, actually we support like to specify in the same SQL different duration for the hopping window, as well as like different hop duration, the slide duration for different window, as you can see in the window duration and the hop duration clause. Yeah, and similarly, like basically we will allow like for after running this SQL query, you expect like your row will be actually like unnest into one row will unnest into multiple rows with the added like window star and window end. So in the end, it's the section window. So basically, the recap, a section window aggregate record into a section, which represent a period of activity separate by a specific gap of inactivity and idleness. So similarly, we add like a sessionized keyword in the SQL extension to allow users to specify like the time attribute for sessionize on the key that for the goodbye, as well as like the gap. So next, I'm going to talk about actually how we plan to integrate the streaming SQL extension into Spark and Presto. And so we actually have a few discussion internally. So for tumbling hopping window, currently Presto does not support this concept in Presto SQL. So the idea behind that is like we considering two options. One is to actually like do AST rewrite by using the unless SQL operator. Basically, we can rewrite the tumbling hopping window into the unless clause. And also the other option is we can have a Presto planner to directly support the tumbling and hopping window. So that will require no AST rewrite. On the Spark side, basically Spark has Spark streaming. So the dataset API already provides support for group by on tumbling and hopping window columns. So we can directly reuse that. And for section window, currently both Presto and Spark has no direct SQL support on the section window. So in Presto, we are considering implement the per key section window using the AST rewrite using the lead lag window function in standard SQL. And in Spark, we consider two options. One is the same option that as Presto, to use the AST rewrite, and the second option is basically to use the map group with state API to implement the custom sectionized logic in Spark. Okay, so with that, I think we covered on Extreme how we actually share the same SQL dialect with Spark and Presto in Facebook with the edit streaming extension. So next, we're going to talk about how we actually the query execution. So in query execution, usually there's two approaches. One is the upfront combination. The other is the interpretation. So in Facebook and Extreme, we decide to adopt the interpretation execution approach. To discuss that, and then first let's talk about what they are. So upfront combination approach can be worked as follow. So basically, the query planner will analyze the query, and then in upfront combination, it will actually co-gen the entire C++ pipeline and compile into machine code. The pro of this approach is with all the meta programming and templating in C++. And you can actually really generate highly optimized machine code for performance and efficiency. However, over the time, we actually try out this approach. The problem is you end up generating one binary per pipeline, per stream processing pipeline. And imagine you have to manage thousands of pipeline. It's actually very hard to scale operationally. With each binary for each pipeline. And also we have reliability concern in case of a disaster recovery. Imagine you have to ship multiple different binary all the way to to different machines. And also the C++ build process is usually basically C++ is a compile language. So it heavily rely on the build time optimization. So it usually involves for building each pipeline, it's a very long build process, and this actually result in a low depth efficiency. And the other approach is interpretation based. So the idea for interpretation is basically the query planner will generate the distributed execution plan, and in high level, and then actually each C++ worker node will actually interpret the local execution plan. And then execute the query interpretively. So the pros of this approach is there's no build process needed. So basically, you will just compile, analyzing the query and generate a plan. And also, it has you can share a single engine binary for all the pipeline since it's interpretation, and that makes it easier to scale to manage thousands of pipeline operationally. However, the problem for interpretation is to achieve high efficiency, interpretation usually cannot cannot execute on a row by row basis. So usually you will use actually a vector at a time processing model on the columnar data representation to basically to amortize the interpretation overhead, as well as high cache miss latency, and also leverage the CPU SIMD instruction support in order to achieve high efficiency. So yeah, So I think like we tried the upfront combination approach before, and it turns out that it's just hard to scale. And then interpretation approach, we actually like there's recent effort that in Facebook we are actually build and share the same vector by C++ like SQL with evaluation engine. So we decided basically to adopt the interpretation approach in Facebook for Extreme. So next, I'm going to talk about actually like the part that I just discussed and how we actually build and share the same vectorized SQL evaluation engine with Spark and Presto. So this led to the introduction of a new effort in Facebook, as we call Veloz. So the Veloz is basically a new C++ vectorized SQL evaluation engine. So its purpose is basically to provide a universal state-of-the-art building blocks for all the compute in Facebook. The goal of Veloz is basically we want to achieve high efficiency and low latency, as well as consistency across different engines. If we share the same vectorized SQL engine, evaluation engine across different like batch and stream processing engine, so it's much easier to achieve consistency where you share the same execution logic as well as the same building UDFs. And also the other one is the reusability and engineering efficiency, where we don't need to each team to maintain its own local evaluation engine. So the goal of the Veloz is basically to fully replace the evaluation engine inside Presto, Spark, and Extreme. So on the right side, it basically shows like a brief overview of the architecture of Veloz. So underlying like on the bottom is basically like the vectorized engine. And on top of that is the expression evaluation engine built on top of the vectorized engine. And after that, we build like different SQL operators on top of the expression evaluation engine. And in the end, we have the local task and driver concept to actually manage the memory and also the multi-threading locally for executing the operator chain. So in Extreme, basically we build all our like SQL operators, streaming SQL operators on top of the Veloz expression evaluation engine, and as well as the Veloz vector engine. So here is basically an overview of the stack. So basically in Extreme, we can take in like both core SQL as well as the data frame API. So this is not covered in this talk. So it's like a data frame API is like API quite similar to the Python like Spark data frame API. And we're actually like in the query planner, we fit in this two language, parse it, and then convert to a logical plan and go through the optimizer and the physical, convert into physical plan. In the end, it will be actually converted into a distributed execution plan where each like local node will run a stylus processor that will actually run the actual execution logic. So in each local stylus processor, we basically have a local planner that's the local planning according to the local execution plan for this node, and then we build a bunch of like stylus columnar operator for source and sink as well, like on top of the Veloz engine. And then underlying is the stylus framework for actually implementing the all the basic like stream processing logics. Okay, so actually we also like did one thing like people might be curious, like how's the performance performed for the interpretation. So we actually did some preliminary like performance benchmark to verify the performance of the new interpretation engine on Extreme. So we basically did a performance study between the interpretive execution model that we built on top of Veloz, comparing to the whole pipeline optimized code gen with the upfront combination approach. So basically, like we compare the throughput and CPU memory footprint during the two different scenarios. One is like normal stream processing with like 10-second mini batching. And also like the other one is actually catching up a 3 days lag where we actually allow the mini batching to be larger. So we saw that in some preliminary result, like using like the projection filter and lookup join operator, we actually see that like the interpretation perform like as well as the compilation approach. And also we see like a 10% to 30% like memory saving. And also during the catching up lag, where we actually allow like a larger batching to be used, we see that interpretation beat the combination like approach by like 30 to 50% in throughput, and also with same CPU and less memory usage. Okay. So looking ahead, I think in the future, like I think both Extreme, Core SQL and Veloz right now are still really in active development. So there are many challenges still remain to be solved in Extreme. So that include like how do we do efficient native streaming window aggregation on top of Veloz? How do we do efficient like a native streaming join on top of Veloz? So how do we do like a fast state warm up and etc. So yeah, and also I think like the Core SQL and Veloz will be also like open source in the future. So we'll be welcome for more people to contribute and use. Yeah, with that, I think that's the end of my presentation. Thank you.
Great, thank you so much, Shuyi. We have a couple minutes right now for Q&A. If anybody wants to drop something in the Q&A channel, we'll also have more time after Marta's presentation. Just take a look. All right, I'm not seeing anything right now. So again, feel free to continue adding any questions you have into the Q&A. And with that, I want to thank you again, Shuyi, and we will, I'll take over the screen share and just.
Yeah, sure. How can I stop?
Oh, and we just had a question pop up in the Q&A, so 2 questions. All right, Shuyi, I will, if you want to join us back for a minute.
Yeah, sounds good. Okay.
I can read this out. So the first one is from Maxim. Maxim says, is Xstream Stylus or Velox going to be open sourced?
Yeah, so I think, yeah, let me answer the question. So so for Extreme Stylus, right now we have internal discussion for open source, but I think it's like not really on the roadmap right now. But I think for Veloz, I think like we do have the plan to open source like start from the beginning, and it's actually like it's a collaboration between Facebook and also another like industry partner. So we do have like a plan to open source Veloz. Yeah.
Great, thank you. And the second question we have here is from Tim. He says, is the e-time parameter unbounded, i.e. continuous streaming?
is the E time? Do you mean, so that means the event time? I assume that is event time. Yeah, this is this is continuous streaming. Yeah. So basically like in order, however, like we do like in order for to amortize the interpretation overhead, I mean, we do require like a mini batching to be applied so that like to actually amortize the interpretation overhead or the like dynamic like dispatching overhead in C++. Yeah, but it's a continuous streaming. Yeah.
Okay, great. All right, it looks like those are the questions we have right now. I'd love to go ahead and introduce Marta. Marta is a developer advocate at Ververica and a contributor to Apache Flink. Before finding her mojo in open source and streaming analytics, she worked as a data warehouse engineer at Zalando and Accenture. So welcome, Marta.
Thank you. Hi, everyone. Should I share my screen?
Yes, you should be able to.
Okay, cool. I'll take it away then. Thank you, Carolyn. So hello, everyone. Like Carolyn gently introduced me, I'm a developer advocate at Ververica, and I've been involved in the Flink community and working really closely with a big chunk of the Flink core maintainers for around 2.5 years now. And one of the things that is still hard for me to this day sometimes is to keep up with the level of integration that we have with all the projects in the same ecosystem as Flink. And so what I wanted to talk to you about today, or to give you today, is an overview of how the integration between Flink and Pulsar has evolved over time, where we stand today, and a bit with more of a focus on the SQL side of things. So I'd like to start first with a little background on the why this integration makes sense, because a lot of times you get comments like this where people tend to reduce everything to open source turf wars. And what is in the end the value to the open source community of Flink tightly integrating with Pulsar, and why does it make sense that these two projects work closely together? If you look closely, like both projects share a pretty common vision, or a common understanding around the idea of unifying batch and streaming under one system. And on the Pulsar side, how this happens is streams are seen as this unified view on data. And on the Flink side, batch is considered just a special case of streaming, or like a subset of streaming. And a quick recap on what all of this means in context. So in Pulsar, the data is abstracted as infinite segmented streams. And it basically provides two levels of abstraction. So a pub/sub messaging layer for streaming, and a layer for durable storage and offloading. So a data processing engine can use either of these abstraction layers to process the data in whatever is the most efficient way for each of them. And this is where Flink comes in. So as a streaming first data processing engine that can also do efficient batch processing. And why is it important, or why is the Flink community working towards achieving unification? So the whole idea is to allow users to reuse code and logic across batch and stream processing use cases. So eliminating a lot of redundancy, and also making sure that the semantics stay consistent, so that people don't have to learn a completely new API for each processing mode, or for the level of abstraction that they are choosing to use. Another advantage, or another reason why we're pursuing unification, is so that you can also only operate one system instead of disparate systems for the two execution modes. and ultimately also unlock new use cases that mix historic and real-time data. Like if you need to bootstrap a job with historic data and then switch to streaming consumption once you're caught up. And the main differentiating use case for Flink and Pulsar, or like to have this combo of Flink and Pulsar together, is then to really simplify building a unified data processing stack. So for example, instead of building something following the principles of Lambda architecture, where you have like a speeding layer and then data stored on Hadoop to process in batch or something like that, we can just combine these two technologies into a single stack for storage and processing for both real-time and historic data. So with this little introduction, I mainly wanted to make the point come across that it goes a bit beyond than just wanting to build project X or Y. There's actually a purpose to these communities working very closely together, because they share a common vision and can benefit from each other. Okay, so now that we have an idea of why you would want to use Flink and Pulsar together, or where these two projects are going, it's also important to just mention why we'll be focusing on Flink SQL today and not everything else in Flink. Because Flink is, in the end, very broad and supports a lot of different use cases across a lot of different industries and scales. And so today we'll focus more on the use cases that are enabled by Flink SQL, which is the higher level API. So as a user in Flink, you have a choice in APIs that will trade off basically how easy they are to use and how expressive you can get with them. So for more higher level or domain specific use cases, there a lot of times are a bit closer to this relational way of thinking about data. It's sometimes much more convenient to just express problems in rapid prototyping languages like SQL, and also let all the heavy lifting be taken care of for you. So you don't really want to be thinking about state management and this sort of details, because here the focus is really on working on your logic to meet business requirements, not so much on implementation and maintenance. And these are also the use cases that I was mentioning before, where you might have mixed batch and streaming workloads. And in the end, the goal of using an abstraction like Flink SQL is to maximize developer speed and autonomy, basically make an advanced stream processor like Flink more accessible to everyday use, but also with less overhead, even if you're a Java or a Scala person. So in the real world, some examples of these use cases are giving users the tools to build unified pipelines for online and offline model training, like they're doing at Weibo, allowing them to independently build end-to-end streaming analytics pipelines without really having to depend on an engineering team or an operations team, like what Uber is doing with AthenaX. And another example is Criteo, that just has an internal platform where people can just use Flink SQL to generate features for machine learning model training. And the nice thing about providing a SQL-based API to do streaming is that is exactly what I was mentioning before, that basically everyone knows SQL. So if you've used the database before, you'll recognize this query as just ANSI SQL. And this means that you also know how to use Flink SQL from the get-go, which may not necessarily be true for the other Flink APIs that use Java or Scala, or just really require that you get too much in the weeds of Flink itself instead of really focusing on the business problem that you're trying to solve. So what's different about running SQL on top of a streaming engine compared to, for example, a relational database? So in your regular database, you execute your query at a certain point in time. So the engine takes a snapshot of the table at the time that you submitted your query, and then it just computes the results based on that static snapshot. And then a final result is produced and the query terminates. If in the meantime, new data arrives in the table, this is not considered to your final result because the engine is operating on, just on top of the snapshot at query time. On the other hand, in streaming SQL, your SQL query will be continuous and never ending. So the first thing that you do is you deploy your query, and then whenever data is added to the table, the changes are just continuously ingested. And in the same sense, the results are also continuously updated. So at this point, which was the point where we did the query or we submitted the query before, the results are exactly the same. But the difference is that if new data arrives, it's also considered and not just ignored like before. So this query will keep on running forever until it eventually fails for some reason, or if you just cancel it. So in a nutshell, very quickly, what Flink SQL gives you is a high-level relational-like way to query data streams using a language that you probably already know, and that is fairly common, even if you're not an engineer. And it's optimized to handle batch and streaming workloads in a unified way. So a lot of times, you can use the exact same query to process real-time data and say a file stored in a S3 bucket. Or in this case, probably not right now, but in the future with Pulsar, you'll be able to just seamlessly switch between querying Pulsar streams and segments without really having to change your logic at all. And besides all the operations that you might be familiar with from SQL databases, so like joins and aggregations and filters, Flink SQL also has support for advanced operations like time traveling, support for change data capture, pattern matching with match recognize, and other very powerful functions. As well as you can easily extend it with UDFs using whatever language you want. So you can do Java, Python, or Scala UDFs. You can bake your own logic into your SQL queries. And this means that with something as simple as standard SQL, like you saw so far, you can build applications that with the same performance, scalability, and consistency guarantees as any other Flink program. And you have a whole ecosystem around it that makes it really easy to write end-to-end streaming applications using nothing but SQL, little Java, little Python, little Scala if you want. And Pulsar is very much part of this ecosystem, and kind of the reason why we're all here today. And so I wanted now to just have a bird's eye look into how the integration between Flink and Pulsar has evolved over time. So the first efforts to integrate Pulsar and Flink date back to around 2018. So that was Flink 1.6. We are now at Flink 1.12. And the first iteration of this effort was pretty basic. So it was more about plumbing than using Pulsar as a storage system. And in the next iteration, a lot of work went into really understanding what a tight integration could bring, that could bring the best of both worlds would look like. So the first thing was to bring schemas into the picture and then make table API / Flink SQL as first-class citizens of the connector. So this allowed already back in 1.9, that you could easily run Flink SQL queries on top of Pulsar with little configuration needed on your side. And more recently, so like I said, 1.12 is the most recent and the stable release right now. The Pulsar community worked on a bit more advanced features already. So the support for Pulsar and Flink is coming to a really very complete state. And so in 1.12, you now have things like end-to-end exactly once guarantees and support for upserts. Like if you want to consume and interpret change logs, you can now do it from 1.12. And there was also a good number of improvements that reach these users of Table API and SQL, like the ability to read and write metadata from Pulsar messages, things like event time, keys, customized fields. You can now also use computed columns. You can define watermarks. So I will show you just a small taste of it in a little bit. And looking slightly into the future, 1.13 is getting closer and closer. The feature freeze will be somewhere around end of March. Are we in March? Sorry, I just got confused about time. Around the end of this month. And so Flink 1.13 should be out somewhere between April and May. And what is being discussed for this new release is to actually contribute or get the contribution in for the connector into the core Flink repository, because right now it still lives in an external repo that is maintained by StreamNative. And another discussion that's also ongoing for this release is porting the connector to the new unified source API, where then you'll be able to handle, or the connector will be able to handle batch and stream ingestion. So what I wanted to show you to finalize or end this talk is how you can make use of this evolution to put together a very simple analytics pipeline. So we'll consume some data from Twitter into Pulsar, do a very simple aggregation, and then sync the results to Pulsar again with some things in between. So first, what we'll do is we'll use the Twitter Firehose built-in connector to consume tweets into a Pulsar topic. And you can also just do a quick check after creating the source that we're actually getting tweets in and that our topic is being populated. And then next we can start the Flink SQL client, which is a client that is in open source Flink. You can just spin it up and use it. And what we'll do, you can spin it up and use it to just submit SQL queries to a Flink cluster. And so what we will do is we will use a Pulsar catalog to access the topic directly as a table in Flink. So we will tap into, we will directly use the SQL, the Pulsar catalog to get, for example, access to the schema of our tweets topic. And this will make some things a lot easier moving forward, like you'll see. So yeah, as you can see, again, everything is basically statements that you would know from working in any database. So like show tables and yeah, just change catalogs. And then you can also do just a select star directly from the topic, and you can see that you can already see the contents of your topic in Pulsar as a table in Flink. So you can, this is the result of doing a select start. And yeah, you can see that even though we're just using the catalog, we didn't really create any table ourselves explicitly. This is already treated as a Flink table. But then when you actually ingest the data, you kind of get disappointed and find out that most Firehose events come with a null created time, which means that right now we don't really have a notion of time in our application. So what can we do to actually fix this? And one way to get a relevant timestamp is to use something that I mentioned before, so we can extract metadata from our Pulsar messages to get the published time. So this is the timestamp of when the message was published. And the really cool thing about having an integration with the Pulsar catalog is that now you're able to create a table with the exact same schema as the original topic by just using a create table like statement. So you don't need to explicitly define all the columns and data types. Like all this conversion is already is done for you between Pulsar and Flink types and this kind of thing. You here we are just defining the we are just defining this column that we want to this metadata column that we want to bring in as a computed column, and then we are defining a watermark on it so that we can deal with it in event time, or we can use it as the event time to kind of reason about time progression in our application. And yeah, to create the table, you see it's just regular SQL DDL. We're using the Pulsar connector, tapping into our tweets topic. So I'm basically looking and describing the connector properties. This is probably the part that may look a bit more alien if you're used to regular SQL, but in Flink SQL, every table is backed by some system. And so we need to always define the connector properties. And here we have a table that is backed by Pulsar topic, and we are using our topic has a JSON schema, so we are using the JSON format to serialize the messages. And same as before, I just submitted this statement using the SQL client, and we're good to go, and we have a table created. And because we're using published time, and yeah, like I said before, defining as a watermark, we finally have some notion of time in our application, and we can move on. And to close the loop, like I said, this is not an actual extensive or very intricate demo. I think there's already a lot to absorb, especially if you've never heard about Flink SQL or Flink before. So to close the loop, we can just create a sync table that is again backed by new topic in Pulsar, and we just insert into it using a simple windowed aggregation. So here you can see that the query is pretty much something you could run on any database, just standard SQL doing some aggregation of the total number of tweets over windows of 10 seconds. And once we submit this query in the client, it will run continuously and continuously sync the results into Pulsar. And once you run this insert into statement, you can actually I forgot to include it, but you can actually open the Flink web UI and you can see that an actual job was submitted to the cluster. And that is just running there. Cool, and so what you should see in your Pulsar topic on the new tweets ag topic we created is exactly, just a count of tweets in windows of 10 seconds. They will come in and it will be appended to your topic as time goes by. So time is short, and of course there's a lot more to explore and to do with Flink SQL. It's very powerful, and even if you have the knowledge to use the other APIs, sometimes it's just much quicker way to do some exploration, or yeah, just to put together a pipeline with very little overhead. Oops. And so if you're interested in learning more about Flink SQL and actually see more elaborate and interesting examples, we at Ververica created recently a Flink SQL cookbook where we share regularly hands-on examples and patterns and use cases for Flink SQL, like some of the examples you can see here, like how you can maintain materialized views with change data capture and Debezium, just do n-way joins, or detecting patterns in real time with match recognize. There's a lot of interesting stuff. The support of SQL in Flink is very, very broad. And yeah, that's all from my side today. Thank you.
Great, thank you so much. That was a really helpful overview. I learned some things, a lot actually, so that was really great. I want to open it up for questions, and we have one right now in the Q&A, which I'll read in just a minute. But if you'd like to raise your hand, we'll unmute you, and you can ask Marta directly. So first question we have is from Adam, and he said, how is Flink different than Spark? Sounds like Flink is a processing engine platform for both batch and streaming.
Mm-hmm. Yeah, I think that's a very, very common question. There's always the Flink versus others. The thing with Flink and Spark, I think that the fundamental difference is that Spark was originally a batch engine that then tried to build functionalities to also do streaming, and Flink was the exact opposite. Although in theory it started as a batch processor, but Flink was always built from the get-go for streaming and to do one at a time event processing. So you can get you can just get a lot of different qualities that you can't get with Spark, even with Spark structured streaming, because in the end, under the hood, they're still doing mini batch, everything by mini batch. And yeah, Flink is just as real as stream processing gets.
Hi guys, this is Girish from Uber. I can also pitch in a little bit here. We have both Spark and Flink at Uber, and we can use it for different use cases. So as Marta mentioned, Spark is primarily focused on batch use cases, and Flink is real time. That's the way it has been. But often when you're doing real-time pipelines, you need to do backfills for one reason or the other, right? So your jobs got restarted, or you're trying to bootstrap your data, or whatever. There are multiple reasons. And we actually found it to be easier to take the Flink engine and use it to backfill data rather than trying to recreate the entire pipeline in Spark just for the backfill or batch mode operation, if you will. We've also shared some of our work. If you Google for Kappa Plus, that's what the architecture that we're using is called. You can see more details about this. There are some nuances there. You need to make some changes in the way you're using Flink for batch mode. But actually, Flink is pretty good at large-scale data too. It has some inherent advantages. For instance, it's always on. It's pipeline execution versus like batch mode, where you can only do one batch at a time. You don't have to do like saves into disks, which you'll have to do with something like Spark. So there's a lot of inherent advantages with Flink. But again, I think from Uber side, our approach is if you're doing real time, we start with Flink, and then if you need to do backfills or any other batch, you can actually make Flink do that. But if you're doing batch mode, or if you're doing like some stuff that Spark has good libraries for, maybe Spark is a better starting point. So hopefully that also adds some context here.
Thank you for that. Some added color. Great. We have another question. This is, does Flink SQL have automatic resource planning, such as the parallelism or memory setting? And the same question to Xstream.
So maybe I can only speak for Flink SQL. You have in Flink SQL you have some defaults that are reasonably set if you don't want to have to tune it, and then everything is you can always configure it to whatever values you need. So I don't know if you just mean parallelism, memory settings. This is all configurable in the in the configuration YAML file. So you can set it yourself to whatever, just in the same way as you would with any of the other APIs.
Okay, great. Thank you. Shuyi had to drop. We will be sharing his contact information in the slide. So if you want to follow up with him directly. The next question is, where can I find some other Flink users to chat about potential use cases and to ask questions?
So yeah, right now the community mostly gathers in the Apache user mailing list. So you can find in the Flink website there's a community section, and then you have how to subscribe to this mailing list. We are currently exploring other options for this, and usually there's also annually a big conference called Flink Forward, which now unfortunately is online, but that's also kind of the big event in the Flink community. But anyways, you can always just follow Flink on Twitter. We do a couple of meetups, or like this one, but also things like release previews and this kind of thing, where you can also gather and meet people from the community.
Great. Do you guys have a date for Flink Forward? If people can put that on their calendar? Not yet. Okay. Awesome. Well, we still have a couple of minutes. So, okay, we have another question. And also feel free to raise your hand if you want. We can unmute you and you can ask it live. The question is, with the use of Pulsar as the SQL data store feeding into Flink, could you please go over some reliability considerations when making this change and removing the other SQL data stores?
Yeah, I actually don't think I can answer this because I don't know enough about Pulsar, but okay. We have CJ here, so I think
let's see.
Okay, sure, I can take this question. I don't think it's a replacement of the other kind of sources. It's more kind of treating Pulsar as one of the I would say storage, streaming storage for Flink, so then you can query the data there. It's not aiming for replacing other kind of storage system. It's just more targeting for the streaming use cases. Hope that kind of give the idea. And from reliability consideration perspective, I am not kind of sure what would be the kind of reliability questions that you are expecting for, but I'm happy to kind of talk with you, like if you have more concrete idea about what you are looking for. But in general, I want to kind of add one note there is Pulsar is using kind of the cloud native storage for tier storage. That means we are using a lot of existing open standard, like as a storage format for storing the data in a tier storage there, and that would kind of simplify like how a data processing engine like Flink access the data, which it doesn't kind of completely rebuild the system, but we like Pulsar is more focusing on providing an unified streaming view over your streaming data and historical data. Hope that kind of give you a bit idea happy to talk with you more, like once you have more clarification about what are requirements you're looking for. Thank you.
Awesome. Thank you, CJ. And just to introduce CJ, since we didn't do it at the beginning, but he is one of the original developers of Pulsar. So if you do have some Pulsar questions, now's a great time to ask it. He's also the CEO and co-founder of StreamNative. So one thing Cato just shared with the panelists, I'm going to go ahead and reshare it to panelists and attendees. So this is from Cato. Okay, that is not the message I was trying to copy and paste, sorry. Here we go. I'm giving you guys my speaker notes. So Cato said, also, if you have opinions on the Flink community, we're doing a survey that just opened, and she provides a link here on Twitter. So I wanted to go ahead and share that with the attendees on the call as well, on behalf of Cato.
Cool, thanks, I appreciate it. Yeah, feel free to let me or Marta know if you have any questions about that.
Cool. All right, a couple more minutes. Any other questions for Marta? Awesome. Well, Marta, if you want to stop sharing, I'll go ahead and actually just
Yep.
share this closing slide. Perfect. And really, this is just an opportunity. Again, we want to thank, let's shut this Q&A. We want to thank all of our speakers over the last couple of days. Kurt, you can find on LinkedIn. Peter, we have his Twitter handle here. Nang, we have his Twitter handle again. Shuyi on Twitter, and Marta, your Twitter handle. So thank you guys again. I guess just as a final wrap up, if you have any questions on how to get involved in the Pulsar community, you can find me in the Pulsar Slack channel. You can also reach me via email, carolyn@streamnative.io, and happy to talk more about the Pulsar Hackathon, the Pulsar Summit, or any of the trainings that we have upcoming. So if there's no more questions, we can go ahead and wrap it up for the day.
Thanks, everyone. Thank you for joining. Have a great day.
Thank you, Garish.
Thank you.
All right.
Bye.
Bye, you guys.
Bye.
Thank you. Bye-bye.